Good afternoon, Professor Tомас Шюкер. I'm very happy to see you. My name is François Igor Evgenievich Pris. I work at the Institute of Philosophy of the National Academy of Sciences of Belarus. Thank you for accepting my invitation to give an interview and to tell about your research work. So, you are Professor Emeritus of Theoretical Physics at the Center for Theoretical Physics and Экс-Марсель, Université, France. You are currently working in cosmology, but you have also worked in high-energy physics for a long time. You are a specialist in the standard model of particle physics, which describes all interactions except the gravitational one. In particular, you have applied one of the most sophisticated mathematical theories, Alain Connes' non-commutative geometry, to study the physics of the standard model and beyond. Non-commutative geometry, along with string theory, try to unify all kinds of interactions. So, please, could you tell a little bit about the main directions of your research work, not only the current work, but also a little bit about your earlier work?
Yes, with pleasure. From the very beginning, I was attracted by a common ground between mathematics and physics. Later, as I specialized in mathematics, it was geometry and symmetry groups. In physics, it was particles and cosmology. And still today, I find it absolutely remarkable that the same mathematical tools apply equally well to theories of the very small and of the very large. And this allowed me to switch from one theory to the other. My first publication was on certain Lie algebras of vector fields, differential geometry. And then in 1977, I started the PhD in physics. At that time, the standard model of electromagnetic weak and strong forces, which is also called the standard model of particle physics, had just emerged, and grand unified theories were fashionable. Now, the word grand here is misleading because it's only a unification of 3 of the 4 fundamental forces. But anyhow, these unified theories predicted proton decay. And the minimal version even predicted the proton lifetime. It was just above the experimental lower bound. It was clear that within a few years, new underground experiments like Kamiokande would increase this lower bound and either discover proton decay or falsify this prediction. These were exciting times until the verdict fell, and it killed the minimal version. Of course, there were all the more complicated versions, but they had too many parameters to make any prediction that could be verified within our lifetime. So I left the field in 1983 to turn to gravitational anomalies. Gravitational anomalies are a rather technical subject in quantum field theories. They are said to occur, in general, these anomalies are said to occur when a classical field theory, upon quantization, loses part of the symmetries. And for quantum field theories, anomalies are cumbersome in the sense that they make the theory non-renormalizable, which means that the theory has an infinite number of parameters. Renormalizable theories were studied actively because they make they can make predictions. They only have a finite number of parameters. After a finite number of experiments, you have fixed these parameters, and then any new experiment is subject to predictions. A particular nice class of renormalizable theories were fashionable. The so-called Young-Mills-Higgs theories, gauge theories, and the standard model is a particular example of such a Young-Mills-Higgs theory. Then, sorry?
Just one question. You said
Yes.
that the ground unified series are beautiful, very beautiful series. So beautiful series are not necessarily true. Or maybe if a series is not true, then it is not truly beautiful.
Beauty is in the eye of the beholder.
We will talk about it, okay.
Yes, I would say they were beautiful because of simplicity. There were only few theories around that led to renormalizable theories, theories that can make predictions, and this simplicity is what attracted me. In particular, this exciting possibility to, well, the exciting prediction that the proton is not a stable particle, and that this was within the reach of experimental knowledge at that time.
Okay, okay. So then you did gravitational anomalies, and then non-commutative geometry.
Yeah, non-commutative geometry arrived on the market, and similarly to grand unified models, they gave a coherent picture of now all four forces of the standard model, of particle physics, and of general relativity. At the end, in the beginning, it was only the standard model, but then later on, Kohn also discovered that theory could be extended to include general relativity.
But it doesn't predict the mass of the Higgs boson. The predictions was not correct, yeah?
Well, that was the nice feature. It had a nice prediction that it made the mass of the Higgs calculable. And as you said, this later turned out to be a wrong prediction. But maybe I come to this a little later.
Okay, but also a beautiful theory, I think, non-commutative geometry.
Absolutely. It's like Riemannian geometry of curved spaces, which I always liked a lot. It's much more interesting than flat Euclidean geometry. In particular, since we live on the surface of our planet, which is spherical. So every sailor had to, at least for longer trips, every sailor had to take into account the fact that the Earth is not flat. But you know very well about this fascination, since we worked together on it in Marseille in around 1966, 1967.
That's true, yeah.
Yeah, I was really enthusiastic about it, as much or even more as grand unified theories, because general relativity, which is an absolutely beautiful theory.
This is an algebraic approach. Non-commutative geometry is an algebraic generalization of the classical geometry.
Absolutely, yes. If you want, there was always, since always, and still an unsolved problem is how to formulate quantum mechanics in a curved space-time or in a curved space. And non-commutative geometry was, to the best of my knowledge, the first natural example of in endowing a curved space with a uncertainty principle. And this made me so enthusiastic about Kant's non-commutative geometry.
Okay.
Then later, well, as you said, the discovery of the Higgs boson falsified the prediction of the minimalistic model of non-commutative geometry, and I left the field. And I started working on cosmology. I was not the only one to change from particle physics to cosmology. I have experimental friends who changed fields at the same time for similar reasons, because cosmology, thanks to several experimental breakthroughs, among them underground and spaceborne observatories, turned into precision science, in particular with the discovery of the acceleration of the expansion of the universe, that was in 1990, and the discovery of the anisotropy of the cosmic microwave background in 1992. Again, exciting times. For the experimentalists, it was not that they could use the same mathematical tools they had learned. It's because they could use knowledge about how to treat big data, because big data was necessary in particle physics and is also necessary to treat all the huge amounts of new experimental or observational data in cosmology or astrophysics in more general. And also because photomultiplier, which are essential in particle physics, are also essential in astrophysics. Photomultiplier, they make our eye much more sensible by orders of magnitude. And of course, having a sharper sight, of course, gives you a better resolution, and you see better what you want to observe.
Okay, thank you. Professor Thomas Schüker, in one of your articles, you write that after a century of efforts, we are still lacking a unified model of all basic forces. And we are still lacking a quantum theory of general relativity. And what do you think? Have physicists or mathematicians made a significant progress in the task of unifying all kinds of interactions over the past 2 decades, or in the task of unifying general relativity and quantum theory?
Absolutely. I'm the more the positive guy. I see the nice things. And well, we already talked about the discovery of the Higgs boson. That was in 2012. And that particle was postulated in 1964. And since 1964, many physicists, among them myself and you as well, I'm sure, we were excited and we were waiting for this last missing piece in the puzzle of the Standard Model. The Standard Model without the Higgs is not a coherent theory. So we were waiting for it, but we couldn't say at what mass to expect the Higgs boson. Kohn had a prediction, and well, this is physics. You make a prediction, and then, well, it's either falsified or it's true. Another discovery on the road to unified theories is certainly the discovery of gravitational waves, 2016, predicted almost 100 years before, in 1919, by Albert Einstein himself. Lots of effort and lots of money have gone into this research, and always with negative results. As a student, I was a student in Geneva, after Weber's announcement that he found a gravitational wave with his cylindrical antenna. Geneva University also constructed such an antenna and couldn't find anything. And it continued like this. The suspense was really unbroken until 2016, when the first discovery was announced.
Okay.
Then there was also the image of a black hole that was published in 2019 and computed for the first time in 1979 by Jean-Pierre Luminet. So these are three, for me, major breakthroughs on the road to unified theory.
Okay, I agree. By the way, why do you say that the Higgs boson was postulated? Yeah, because sometimes people say that it was the Higgs mechanism was predicted or even discovered. For example, on the site of the American Physical Society, we can read François Englert and Peter Higgs won 2013 Nobel Prize in Physics for predicting the Higgs mechanism, and so on. Is there an essential difference?
No, I said postulated because nobody could say what its mass was, except a few theories like Kahn's. And it was clear that without the Higgs, the theory, the gauge theory of the standard model was not consistent. So it needed it. It's true that the history was complicated, and we still say Higgs boson, but there were Englert and Braut, who also independently, at the same time, a little earlier, discovered this mechanism of spontaneous symmetry breaking. And later it was applied by, well, Weinberg to the model that has been published before by Glashow and Salam, and only the work by Toft and Weltmann, and they got the Nobel Prize for it. They showed that spontaneous symmetry breaking does not endanger the renormalizability of the standard model.
Okay, thank you. So, if I understand well, Alain Kahn's non-commutative geometry has not lived up to expectations of physicists, has not really worked in physics, has it? Are there any successes in its application in physics?
The minimalistic version made this prediction of 270 GeV for the mass of the Higgs boson, and experimentally in 2012, it came out to be 225. Of course, you could say that's the right order of magnitude. We are happy. But the computations were more precise, but they were also naive in the sense that they used non-commutative geometry for parts of the theory, but the effects of the quantum effects were calculated with the standard theory in Euclidean space, not in the non-commutative space. One of the big hopes of a physicist in non-commutative geometry is that non-commutative geometry is the right theory, not only to understand the standard model, but more importantly, to get a mathematically watertight theory of quantum fields. And this is still an open question. So it was minimalistic. It was not only minimal, it was minimalistic. I say minimalistic to say that it was naive, because parts of the theory were calculated in non-commutative geometry, other parts were simplified and calculated in the usual flat geometry. Okay. Now, you can always say, okay, we have to wait until we have a true, a full quantum theory of fields, but this is still missing. And that still is a hope that non-commutative geometry might be the right mathematics for quantum fields. Okay.
Okay. And actually, there are also other varieties of non-commutative geometries. Are they more successful from the physical point of view?
Absolutely. Before the standard model unified with general relativity, there have been smaller versions of non-commutative geometry. There was the Conlott model. There was a model by Dubois, Violette, Kerner, and Mador, and one by Kokoro and Esposito Fares. They are, it's fair to say they were stepping stones for the development of the more complete theory, but just stepping stones in the sense that they didn't give any prediction. The Conlott model gave a prediction for the Higgs mass already, which came out different, also far away from the experimental mass that we know today. And these theories were not developed any further. In that sense, stepping stone, I would say, is the right.
Okay. And what about string theory and loop quantum gravity? They do not belong to the family of non-commutative geometries. Are they promising? Are they still popular?
I would say that string theory is dying. Now, the death and the birth of theories have timelines, and already Max Planck has a nice sentence about the timeline of the birth of a theory. He said, a new theory is accepted not because the others are convinced, it's because the others die. Mm-hmm. So you need at least one generation. So there's a nice example. You remember well Daniel Kastler in Marseille.
Yeah.
One of the, well, he attracted me to Marseille and introduced me to non-commutative geometry. He did his PhD in 1953 on quantum chemistry in Germany. And then he tried to return to France. France is the native country of De Broglie, one of the fathers of quantum theory. Mm-hmm. And still, in 1953. I mean, the birth of quantum mechanics was 1900. Daniel Kastler had a hard time to find a position. So I think that in Planck's sentence, one must allow for 2, maybe 3 generations until the others have died.
Okay, as I know, quantum physics began to develop relatively late in France, yeah, didn't it? That's why Daniel Kastler couldn't find the position, because quantum physics began to develop late.
Because students of opponents of quantum mechanics were still having their professorship and were still maintaining their hostility towards the new theory. Okay. But now you ask about strings, and it is not that strings had any success. I mean, physical success in the sense of making predictions and that these predictions are verified. On the contrary, strings, in order to be viable, in order to be a coherent theory, they need supersymmetry. However, supersymmetry has been excluded by the LHC by now. And I think that Planck's rule, with the latency extended to, say, 2-3 generations, also applies to the deaths of a wrong theory. Like we have seen the theory of the ether for light had a hard time to die when relativity came along. So my speculation is that superphysics will survive me.
Again, beauty is not a criterion. Supersymmetry is a very beautiful idea, and you say strings need supersymmetry, and it doesn't work. Yeah,
supersymmetry doesn't work. Yeah, I mean, since my PhD time, supersymmetry promises that supersymmetric particles will be discovered in high energy experiments. And each time a new detector was built, it was also in order to find supersymmetric particles, and it never worked. And then they say, well, we have to go to higher energies. They couldn't say to which energy, except that, say at 100 GeV, it becomes already difficult for supersymmetry to live. And then with the Large Hadron Collider, it is, I guess, has become hopeless for supersymmetry. And strings is constructed upon supersymmetry. And
okay. And do these theories, non-commutative geometry, string theory, loop quantum gravity, and so on, do they compete with each other, or do they complement each other?
Well, they do have common ground. Non-commutative versions of strings have been tried. And I think it's fair to say that the results were not encouraging. Loop quantum gravity, Daniel Kastler had invited Carlo Rovelli to Marseille in order to explore common ground between non-commutative geometry and loop quantum gravity. And again, the results were not encouraging, but Carlo has been building a flourishing school of loop quantum gravity in Marseille, and it continues flourishing after he left Marseille last year. So that's one answer to the question you asked before about superstrings. For loops, it's still popular and alive. And
so hybrid theories do not work, or even not easily possible. So maybe they are not beautiful enough, hybrid theories.
Maybe, yes. Yeah.
What about?
But, I mean, they were close enough. It was natural to explore the common ground between loop quantum gravity and non-commutative geometry. From the sociological point of view, you must also know, and you know it, that Kohn and Rovelli are friends, and they have written a paper very early on, a common paper on the time evolution in operator algebra.
Yeah, I've read it. Yeah. Interesting paper. Yeah, and there are, of course, non-commutative gauge theories and so on. So
yes, everything has been.
Now you are working in the domain of cosmology. So what are the major problems in cosmology now?
Well, like particle physics, cosmology now has its standard model, which is called lambda CDM. Lambda standing for the cosmological constant, and CDM stands for cold dark matter. It is always a problem to have a standard model, because then the opinions are polarized. You are either a believer in the standard model or you don't believe in the standard model. So that's for the sociology. Polarization of research, of ideas. Concretely, we have to explain dark matter, because the usual matter that makes up the human body, that makes up the Earth, the Sun, the galaxies, is not enough, has not enough mass to be in agreement with this standard model. And then I personally still have a problem with the cosmological principle. Cosmology has two pillars. One is general relativity, and the other is the cosmological principle that postulates a space of maximal symmetry. But this formulation of the cosmological principle is not relativistic, because the space that is supposed to be maximally symmetric is a space of simultaneity. But simultaneity in relativity is a heresy.
And sometimes people say that the cosmological principle says that the spatial distribution of matter in the universe is homogeneous and isotropic. Is it correct?
Yeah, that's what I meant by maximal symmetry.
Maximal symmetry.
A space of 3 dimension, that's a theorem of differential geometry. Any space, flat or curved, of 3 dimension can have not more than 6 symmetries. And these 6 symmetries in the flat space are what you mentioned, 3 rotations and 3 translations. And this is, the 3 rotations means it's isotropic. There are no privileged directions. And the 3 translations is what one calls homogeneity. And that means there is no privileged point. Okay.
And is there any significant progress in understanding the nature of dark energy and dark matter?
Yes. Dark energy is not a problem. For me, it's not a problem. It's, for most colleagues, it is a problem. For me, it's not.
For you, not. Okay.
No, it has a natural explanation, a beautiful explanation, going back to Einstein. You choose a positive cosmological constant, and then you don't need dark energy.
But it's not too simple as a solution.
Sorry?
Maybe it's too simple.
Too simple. Well, for me, as simple as you can. It's fine.
The simplicity principle.
And then, yeah, and then dark energy, dark matter, well, with the new insights from gravitational wave detectors, dark matter might be explained, maybe only partially, but might be explained by black holes.
Okay.
Dark matter, well, in French, it works better because in French you say trou noir et matière noire. So you say black matter, black holes. And so it's absolutely natural to say, well, maybe these black holes, which were, we were surprised to see as many black holes as we see now with gravitational waves. Maybe they are already sufficient to explain the black matter, which is in English called dark matter.
Okay. And are there any successes in gravitational wave astronomy?
Absolutely. There is one major outcome is that the speed of gravitational waves is measured with very high precision by just one event of collision coalition, fusion of two neutron stars. And from there, we know that the speed of gravitational waves is equal with very high accuracy to the speed of light, which in terms of unifying theories like electromagnetism and gravitation is absolutely capital. It's one solid prediction of Einstein's theory.
Okay.
And now we know it's correct.
Professor Šuker.
But there are many other things that we already find out about the nature, how neutron stars are built and so forth. And it is clear that we have only scratched the surface of a gold mine. I think this will give major breakthroughs in the future.
Okay. Okay. Professor Šuker, do you believe in multiverse? In France, Aurélien Barrault, cosmologist, he is also working on loop quantum gravity. He popularized this idea, the idea of multiverses. Do you believe in it?
Well, my name is Thomas. I'm not a believer. I want predictions and their observational confirmation. And so far, I haven't seen any prediction and, of course, no confirmation.
Okay. And what do you think about the so-called anthropic principle?
Again, I wait for predictions and observation.
Okay. By the way, according to the standard Encyclopedia of Philosophy, as recently as in 1960, cosmology was widely regarded as a branch of philosophy. Some physicists are skeptical about philosophy. Others, on the contrary, believe that philosophy is necessary for physics. Physics needs philosophy, philosophy needs physics. This is the title of one of Carl Ravelli's papers. And what is your opinion, or what is your attitude toward philosophy?
Well, your example shows clearly that there is common ground between philosophy and physics, and it's interesting ground. If you have two schools of thinking and they have common ground, this is always fascinating. I have several friends who enjoy a double career as physicist and as philosopher, and I admire them for exploring this common ground. By the way, you already mentioned three of these friends, Carlo, Aurélien, and François Igor.
Thank you.
Of course, in presence of common ground, you will always have jealous men unwilling to share this common ground. And it is unclear what the position of Richard Feynman was. He's one of my heroes in physics, but it remains open what he thinks. But everybody or many colleagues know a phrase that is attributed to Feynman by a historian of science, Brian Cox. So apparently Feynman said the philosophy of science is as useful to scientists as ornithology is to birds.
I agree, but not vice versa, I think. So,
okay, yeah, but there is an equally critical position concerning the usefulness of abstract mathematics in physics. So here we are at what I was always attracted by, the common ground between mathematics, abstract or less abstract, and physics. And there's this phrase attributed by Feynman saying that physics is to math what sex is to masturbation. So it is clear that he was not very fond of abstract mathematics. He was more an intuitive physicist. He invented the path integral, the Feynman formulation of quantum mechanics. And it's still today not solid mathematics. It's very intuitive, but it's mathematically not well defined. So it's quite clear that he has a more liberal standpoint with respect to abstract mathematics.
Okay. And what do you think about the nature of quantum reality? This is a philosophical question.
Yes, and let me answer with a picture or a little story. Two physicists, let's call them Alice and Bob, meet. Alice says, "I know nothing." Bob smiles. But then Alice continues and says, "And I know that you know nothing." At that time, Bob's smile freezes. But then she continues more and says, "And I know that the others do not know that we know nothing." And Bob's smile makes a timid comeback.
So nobody really understands quantum mechanics. In 2012, the physicist David Mermin, maybe you know him, wrote, "New interpretations appear every year. None ever disappear." So, which interpretation of quantum mechanics do you prefer, if any?
Well, the very naive one that I can teach easily to students. We have an equation, a differential equation, either the one by Schrödinger or the one by Dirac. And we have a dictionary relating the solutions of this equation to observations. And these observations are atomic spectra, cross-sections, lifetimes, and so forth. And this leads to a plethora of predictions and postdictions. And
so, do you consider the scientific theory as a tool for making predictions?
Yes.
Okay.
And maybe it's even the major tool. Make predictions.
Well, this is instrumentalism. Maybe. Okay. And how do you understand the quantum measurement problem?
For me, the uncertainty principle is not a problem. It is a relief. Why do I say that? I cannot believe in a deterministic description of the world. If you want to make correct predictions, you need the possibility to go wrong. And to the best of my knowledge, quantum mechanics is the first theory in physics to introduce a mathematically precise notion of uncertainty. Now, this uncertainty is caused by measurements or by observation. And that seems very natural to me in the following sense. A typical observation is the scattering of light off the object you want to observe. Now, if the object is macroscopic, like a billiard ball, its position and velocity will be disturbed only very little by the scattering of the light that you shine on it in order to see the billiard ball. On the other hand, if the object is not a billiard ball, but is a tiny elementary particle of the same size, of the same energy as the photon, that the light that you use to observe it, then this disturbance of the elementary particle by the light being scattered off it cannot be neglected anymore. Now, to give an example, try to observe a billiard ball, say A, which is at rest on a table, on the billiard table. And you try to observe it by shooting another billiard ball, say S, towards it. If S continues on a straight line, you can say that the other billiard ball, R, at rest, is not on the trajectory of S. On the other hand, if S comes back to you, you can say that the billiard ball was on the trajectory of S, but was in the past, because after it got hit by the billiard ball S, such that this billiard ball comes back to you, it is going to be somewhere else and it won't be at rest anymore. Heisenberg's uncertainty relation can be motivated by this little picture. And this picture, or this uncertainty relation, has been transposed to other sciences like psychology. There, the example is when you ask a person what she thinks about a certain matter, and she answers spontaneously, you will know only what she thought about that matter before her answer. But your question might induce second thoughts in her on this matter, and she might change her state of mind. So,
okay. By the way, quantum correlations also have found applications in the human and social sciences.
mm-hmm.
And the measurement problem, some philosophers think this is the central problem of the philosophy of quantum mechanics. And you establish a close relationship between the uncertainty principle and the measurement problem. But what about the collapse of the wave function? Is it a real process?
I have no idea.
Okay. So there are different philosophical positions: realism, idealism, pragmatism, and so on. What is your position, if any? Are you a realist?
Well, I'm.
So you said maybe you are.
I'm not sure. Yeah, but let me answer with still another picture.
So they complement each other, like in quantum mechanics, wave and particle pictures. No.
Yes, I think they are two different approaches of the same object. But let me give a very naive picture that is, and my understanding has never gone beyond this picture. It's simple. You take a horizontal blackboard, and then nature draws a curve on this blackboard with a piece of chalk. But then nature hides this curve by covering the entire blackboard with chalk dust. And that's why you need a horizontal blackboard. So the dust settles and then hides the curve that nature has drawn on it. Now comes an experimental physicist with a fine paintbrush and carefully removes the dust on a square centimeter of the board, skillfully enough as not to destroy the curve possibly drawn by nature in this particular square, and say that he reports a negative result. Then other experimentalists will work on other squares until one of them discovers a small piece of a line. Then he wins the Nobel Prize. And then comes a theoretical physicist, and he recognizes, of course, immediately that this piece of line is a straight line. And he makes a prediction for what is to be expected at a neighboring square. And indeed, another experimentalist confirms that this extrapolation is correct. And he joins the theorists in Stockholm. And then after many experimental errors and other surprises, the straight line is found to be an arc, but not an arc of a circle. And then come new theories like epicycles or ellipses to better understand what this curve is. And there is a steady go between theory and experiment. Experimentalists discover things, sometimes by chance, sometimes because they follow a prediction, and that prediction might be true or not. And that's the way I see the functioning of physics.
So now I think you are a realist. There is something, a cave for you there in the external world, the ready-made real things, and physicists do discover, not invent them. So maybe you are a realist.
Absolutely. Yeah, discover. So,
and do you believe in the existence of the external world, reality, cognizable by our theories? Or maybe the notion,
yes,
the external reality is a bad notion.
Nature has drawn this curve independently of us, and all we can do is discover it. It's not a creation, it's only, of course, you have to be creative to get this experimental setup working and so forth. That needs creativity, but it's only an instrument. Can I ask you, is realist a compliment or is it an insult?
Sorry?
Since now I discover that I'm a realist.
Could you repeat your question, please?
Yeah, is it a compliment or is it an insult to be a realist?
Neither compliment nor an insult. No, it's just a position, a philosophical position. So it's okay.
Okay.
So for instance, I'm a contextual realist. I think that ontology is sensitive to context. So some people say it's a middle position between strong realism, objective realism, and anti-realism.
Okay.
And what is a scientific theory for you? What is a scientific theory for you?
A scientific theory is a theory that admits verifiable or falsifiable predictions and or postdictions.
And what do you mean by postdictions?
Let me give you an example. When it was discovered that the light emitted by an atom has a discrete spectrum. Spectroscopy was boosted and lots of atoms were, you had catalogs of the spectra of atoms. And theoreticians tried to put some order in these huge body of data. And Rydberg found a very simple formula that could reproduce, say, the spectrum of the hydrogen atom. But it was just phenomenology. And then came quantum mechanics. And with the Schrödinger equation, you could compute this formula by Rydberg. And So in that sense, it was not a prediction, it was a post-diction because the measurements were already done. But the difference is between predictions and post-diction is the chronology. Post-diction has the observation coming first and the explanation of it second, and the prediction is the other way around.
Okay. Do you believe that our best scientific theories are literally true? And by the way, what is truth for you, for a theoretical physicist?
Truth for...
Are our best scientific theories literally true?
I would say yes.
Do you think that truth is correspondence to facts?
Yes, absolutely. Say, if let me give another image. If you have a blind rooster, let's call him Bob again. He's blind, but he works with big statistics. So it happens that he finds a grain. And when he has found one, he carks loudly in order to impress Alice. He wants Alice to think it was not by pure chance that he got the grain. And I would say that I believe that something is true if you can eat the grain, because then you have a benefit, and the benefit is the proof that you did something useful. Now, for the truth itself, for a physicist, I like the sentence by Wolfgang Pauli, which is a joke, of course. In mathematics, he said, in mathematics and physics, there is absolute truth. In mathematics, this is proofs. In physics, it is experiment. Theoretical physics is where there are neither proofs nor experiments. But more seriously, for me, mathematics and physics enjoy absolute truth in the sense of Pauli, and so do mountaineers. A mountaineer, for him, the absolute truth, if he is able to get to the top of a summit, a difficult summit maybe, that others have tried to climb but failed, and he gets to the top. As a reward, this mountaineer who got on the top of the summit, he will enjoy a new view of the world, of the mountains that are around him that people already know, but perhaps he also sees new summits. So this is my very naive way of thinking about truth and reality. The reality is the stone that the mountaineer touches every day. That's his absolute truth.
Okay. By the way, you said that Pauli said there are neither proofs nor experiments in theoretical physics. Maybe it's not a joke. A famous British philosopher, Timothy Williamson, says that there is a continuum between metaphysics, philosophy of science, and highly theoretical physics. In metaphysics, there are neither conceptual nor experimental truths. In more or less usual understanding of this notion. So, but for him, there are metaphysical truths. So maybe
if I say it was a joke, then because Pauli did very complicated mathematics and he knew proofs of the mathematics, and he also knew very well what the experimental situation was.
Yeah, for him it was a joke, of course. Yeah, yeah. And by the way, some people say that there is non-experimental confirmation of string theories. It seems to me Richard David, I don't remember his name.
Well, lots of them.
A lot of them, yeah. Non-experimental confirmation of string theory. So, Professor,
there's one. Con is one. Con said once there's only one prediction in string theory, and that's the dimensionality of space-time. It is true that there's I don't know of any theory that tries to predict that our space-time is four-dimensional. Now, in string theory, they need fixed dimensionality, but it happens to be 10, 11, or -2, but it's not 4.
But you don't believe in non-experimental confirmation of theories?
I do.
Non-empirical confirmation of...
Yes, Einstein, for instance, when he died, there was only few confirmations of his predictions and with huge error bars. Now it's different. We have very, very precise measurements, and these measurements confirm his theory. But he died absolutely sure that his theory is, that general relativity is correct, because he knew that he had to, that there should be empirical evidence for it, but he was sure of it already before, because his theory was without contradiction. Even Newton had a contradiction, a basic contradiction, which is he needed inertial coordinates. It's only in inertial coordinates that his theory was correct, but he couldn't say what inertial coordinates are. So Einstein said, I need a theory that doesn't need any privileged coordinates. And by far the simplest theory that works without choosing special coordinates is general relativity, still today.
Anyway, Carlo Rovelli criticized this idea of non-empirical confirmation of theories. Carlo Rovelli, yeah. So
I will ask him next time what he thinks about about Einstein's certainty about relativity.
In one of your papers, you write that one of the many satisfying features of general relativity is that it allows for many different approaches. And field theoretic approach, geometric, chronometric, gauge theoretic, causal, perturbative, numerical, and so on. So are we talking about different mathematical languages to describe or explain one and the same physical reality, nature, or maybe we are talking about different understanding of the nature of gravity. Maybe the nature of gravity is ambiguous. What do you think? What could you tell about it? Is the nature of gravity ambiguous, or it is the same nature but just different approaches to the same phenomena?
Let me be ambiguous. My answer, or my point of view, is that these different approaches to general relativity are just different routes demanding different techniques to the same summit. And the summit is the common ground of the different routes. It's there where the different routes meet. So in our example, this summit is general relativity, and you can if you know well field theory and know nothing about geometry, you can get to the top of the summit. If you know well geometry, you don't know field theory, you can get to the top and you can meet your colleague and you can shake hands with him at the top. And this is very nice.
But do you think that the summit is already there, ready-made, predetermined?
Yes,
Okay.
yes, absolutely. Like the summit is solid rock, it's there before we are born.
So maybe you are a metaphysical realist.
Oh, good.
By the way, are gravity and space-time the same thing for you?
No,
is it the same? No.
Space-time is the arena in which force fields like gravity or others, electromagnetism, or other gauge forces play. So it's just the setting in which the forces play their game.
Okay, but from a geometrical point of view, gravity is the curvature. Well, roughly speaking, it is space-time, not force.
Yes.
From a geometrical point of view.
Yeah, but the metric is a field, so you can also say it's a field.
Okay. So
but the space-time, I mean, you can talk about spaces without talking about forces. But this is becoming difficult because, I mean, if you have a space and you don't have a force, you might want to talk about the distance between 2 points, and relativity tells you that you shouldn't try to talk about distances.
Okay, so for you we have two entities, space-time and gravity.
Yes.
Okay. So, Professor Schüker.
I mean, I can make it. I can make it mathematical. Space-time is a differential manifold, and this manifold may be equipped, may not be equipped with a Riemannian metric or pseudo-Riemannian metric. So, space-time is the manifold, and this manifold is then equipped with a metric. This metric gives the force, and then you can equip it with other structures like an electromagnetic field.
Okay, okay. Now I see. Okay, thank you. So, Professor Thomas Schüker, do you think that physics is in crisis now? Some people think so.
I know, but I think the contrary is true. And it's more than just thinking, it's a feeling. When I started physics, I was afraid that it would be the bad choice for me. And then only, say, 5 years later, when I got my first diploma, I said, well, at least I was afraid that it was too difficult for me. I wouldn't get on top of it. After 5 years, I saw that this was not the problem, but still there was the problem, would it make me happy? And this only now, after being retired, I can say with certainty, yes, I enjoyed it a lot. And I enjoyed it because of the discoveries. The discoveries, of course, already the ancient discoveries, Archimedes and so forth, is absolutely fantastic. But if you go to the cinema and you want to have some suspense, you don't know, will they find the culprit or not? Will somebody be killed or not? And this suspense was always there. And I had the joy to witness major discoveries. So it's like a good crime story. And my list starts in 1979, was the discovery of the slowdown of the binary pulsar PSR 1913 plus 16. Hulse and Taylor got the Nobel Prize for this discovery. But what is even nicer is that the computation of this slowdown in general relativity, pure general relativity, was done in 1981 by Thibaut d'Amour. Only 2 years later, Thibaut d'Amour made a detailed computation that showed that this slowdown was caused by gravitational waves. It was the first experimental proof, indirect proof of gravitational waves. The next breakthrough was in 1983. I was in Geneva at that time. The discovery of the W and the Z gauge bosons that were predicted already in 1968 by Glashow, Salam, and Weinberg. Then 1990, the discovery of the acceleration of the expansion of the universe. 1992, the discovery of the anisotropy of the cosmic microwave background. 1998, the identification of a supermassive black hole in the center of our galaxy. Very nice movie that proved that there was a black hole. The movie was the sun's orbiting around this black hole, which itself, of course, is invisible. 2012, the Higgs boson, we talked about it, that had been postulated already in 1964. 2016, the direct discovery of gravitational waves, predicted almost 100 years earlier by Einstein, and used today as a new window on the universe. And 2019, the image of the black hole that had been computed in 1979 by Jean-Pierre Luminet. So each time it was exciting. There was the theory, and the theory was beautiful, was simple, and you could think, well, maybe this is right. But as I've told you, there are also cases where the predictions were wrong. And okay, you can't win every time, but there are enough successes. So I can say, retrospectivement, it was a nice life as a physicist.
Okay, thank you.
However, I should also include a negative note. I see one setback. There was this formidable progress from epicycles to renormalizable theories like Yang-Mills Higgs theories and the Standard Model. Epicycles have an infinite number of parameters because you can add as many epicycles as you want with different radii. Then John von Neumann said, and we want more than just a finite number. We want a small number of parameters. John von Neumann said, with 4 parameters, I can fit an elephant. And with 5, I can make him wiggle his trunk. So he made fun of theoretical physicists that each time they got a prediction wrong, added another parameter to explain why this prediction was wrong.
Do you mean
but
that?
Nevertheless, sorry?
do you mean that the normalization procedure is not conceptually well understood?
Well, that's a problem. But it's an algorithm which is
because
allowing
what about
us...
the work of Kohn and Kramer on conceptual understanding of normalization, of perturbative normalization?
Yeah, this is what I mean. This perturbative. Well, what they did is they simplified a very complicated computation in renormalizable perturbative quantum field theory, and linked it to Hopf algebras. And the Hopf algebras, they are close to non-commutative geometry. This is why we were very excited about that discovery.
Okay.
But it's the same story. And so we are very satisfied having theories with a finite number, and if you may ask for more than a small number of parameters. And nevertheless, theories with an infinite number of parameters, like epicycles, are making fashionable comebacks. And as examples that are very fashionable and have an infinite number of parameters, I see inflation, very popular. Dark energy, we talked about dark energy. Dark energy has an infinite number of parameters, well hidden, but they are there. Mond theory, modified Newtonian dynamics, has an infinite number of parameters. And there is one family of parameters called f of r, a function of the scalar curvature, to replace to generalize Einstein's general relativity that only has two constants, Newton's constant and the cosmological constant, and nothing more. So this is, for me, completely ununderstandable how one can go back to theories like epicycles.
Okay, thank you. Professor Schüker, and what do you think about the role of beauty in physics? For instance, Sabine Hossenfelder, a German physicist, by the way, published a book entitled Lost in Math, How Beauty Leads Physics Astray. It seems to me in English it was published in 2018. So according to her, the universe is messy and it cannot be described by a beautiful theory. Frau Hossenfelder thinks that there are problems in physics. And this is because physicists use outdated notions of beauty. And but she believes in new forms. She believes in new forms of beauty. New ideas will come with their own forms of beauty. But currently, physics is in crisis because of these outdated forms of beauty. What do you think? What do you think so? Do you think so?
Well, I already said that beauty is in the eye of the beholder. It's very personal. If a flower or a woman is beautiful or not. Leonardo da Vinci, of course, he knows much about beauty, and I like his citation. He says, simplicity is the ultimate sophistication. He doesn't talk about beauty, he talks about sophistication. Then on the other hand, we have Werner Heisenberg. He has a nice sentence saying that not only is the universe stranger than we think, it is stranger than we can think. So he's not talking about ugly or messy, he's talking about strange. Okay. And then John von Neumann also has an opinion about it. He says, truth is much too complicated to allow for anything but approximations. So I think we can agree and say that the world or the universe is complicated. And complication is maybe source of the charm when you try to observe it. If it's too easy, if it's too transparent, then you don't have to make an effort to see and understand, and it's boring. So I wouldn't say that the universe is ugly. However, I would say that our world is being made ugly by man.
I agree with you.
Yeah, and I would like to cite Bertrand Russell, another philosopher that is at the same time mathematician and physicist and whatever. His citation is, in universities, mathematics is taught mainly to men who are going to teach mathematics to men, who are going to teach mathematics to, and so forth. Sometimes it is true. There is an escape from this treadmill. Archimedes used mathematics to kill Romans. Galileo improved the Grand Dukes of Tuscany's artillery. Modern physicists, grown more ambitious, try to exterminate the human race. It is usually on this account that the study of mathematics is commended to the general public as worthy of state support. This is taken from Human Society in Ethics and Politics from 1955. I think that today we may add to the picture engineers and the climate catastrophe.
Okay. Do you believe in the existence of fundamental theory of everything?
I do not believe in any theory of everything, beautiful or fundamental or whatever. And I have a nice example to tell you, which is quite well known. In 1874, Max Planck was a young student, and he started his studies of physics, and he had a supervisor, a physicist by the name von Jolly. And this guy tried to dissuade Planck to do physics. And his reason was, in this field, almost everything is already discovered, and all that remains is to fill a few unimportant holes. Well, we are happy that Planck disregarded his opinion and discovered a new world, not just a little hole, a new world that is the world of quantum mechanics. And then later in the 1970s, I think it was, Stephen Hawking repeated more or less what von Jolly said, that we have the theory of everything, and he thought that supergravity was that theory of everything. And of course, he couldn't have been wronger than betting on supergravity.
Okay, thank you. And what do you think are the most important problems in physics at present?
Certainly understand quantum mechanics. Feynman said, I think I can safely say that nobody understands quantum mechanics. And I think it's still true today, despite a major breakthrough in quantum mechanics, which is quantum entanglement. And quantum entanglement is not only abstract physics, it is already used at a commercial level to encrypt. The first time it was bought by a bank, a Swiss bank, to send and to encrypt. It was tested there to encrypt exchange of communication between a bank in Geneva and a bank in Lausanne, just some 100 kilometers away.
But What would it look like, understanding quantum mechanics? What do you mean by understanding as a task?
Well,
so we don't understand, but...
Well, you asked me the question and I said, I don't know. That was the question, the collapse of the wave function, or the passage from the quantum world to the macroscopic classical world.
Okay, I see.
This is not understood, and in 200 years, you wake me up. What is the first question I would ask? It would be, well, what about quantum mechanics? They understand quantum mechanics now?
Okay. And what are, in your view, the prospects for development of physics?
The immediate prospects are
the prospects.
Gravitational waves, this new window, and quantum entanglement is also opening a window on a new world, and certainly this world will be explored like this blackboard, guided by some theoretical predictions that we have, that the different schools of quantum mechanics have, and by falsifying them or verifying them, there will be progress, I'm sure. And
what are your plans for the future research?
I'm trying to finish, we are trying, and we as theoretical friend, Galliano Ballon, who is retired as well, and an experimental friend, André Tilquin, who is not yet retired, but soon. We have been working together on that subject since years. It concerns a minimal symmetry breaking of the cosmological principle. That won't solve, in parentheses, that won't solve the problem of reformulating in a relativistic fashion the cosmological principle. It's just a minimal symmetry breaking.
Okay, thank you. Professor Thomas Schüker, thank you very much for this interview. It was my pleasure to discuss with you. All the best for you and for your research.
Well, I thank you for your kind invitation to this interview.
Bye-bye.
Bye-bye.